So to recap our journey thus far in trying to prove that the area underneath the Dirac delta function is equal to 1, we gave a kind of visual understanding that all the Dirac delta function is the normal distribution. And to prove that the area underneath the Dirac delta function is equal to 1, we therefore need to prove that the area underneath the normal distribution is equal to 1. And we've done some groundwork for some tools that we want by our side when we go to evaluate this integral over here. And there's actually a little bit more groundwork that needs to be done. And to do that, I'm actually going to defer to another video. A link for that will be provided in the description. But it's Professor Leonard. If anyone's seen a Calculus 3 video on YouTube, I'm sure they've heard of this guy. He is fantastic. The one video I'm specifically going to reference to is the Calculus 3 lecture, and it's about doing double integrals over polar regions. So if you don't feel super comfortable with multivariable calculus, and more specifically doing double integrals over a polar region, I highly suggest you go watch that video for the next part of this proof, where we're actually going to go through and evaluate the integral to determine that area underneath the normal distribution. So with that said, let me pause for a second and write out all of the integration and setup. All right, now that I've written all that out, here we can see I'm making the claim that the area underneath the normal distribution is equal to 1. And one of the simplifications I'm going to do immediately is I'm going to say let mu equal to 0. And the reason why is because in the specific case of the Dirac delta function, this actually is 0. If you remember from the first video, when we changed this value here, it either caused it to shift left or to shift right. We want the Dirac delta function, well, the Dirac delta is defined to be centered right at x is equal to 0. So I'm going to make that simplification because it makes the math a lot easier. Truth be told, I actually don't know how to solve this integral without making that simplification. So moving on, I'm going to make this simplification. I'm going to rewrite this integral. Okay, 1 over sigma square root of 2 pi times e to the minus 1/2, and then we'll just say this is x squared over sigma squared. Okay, forgot my dx there. We are integrating with respect to x, and we're going to keep saying that this is equal to 1. Okay, so let's do some simplifications. Let's pull this guy, I guess this guy right here, out of the integral, since we're not integrating with respect to sigma, and 1 over the square root of 2 pi is just a constant. We can actually just pull out this entire boxed term over here as a constant outside of the integral. So let's do that. So that would be 1 over sigma square root of 2 pi times the integral from minus infinity to infinity of e to the minus 1/2 x squared over sigma squared dx. And we're still going to say this is equal to 1. And I am going to do something. I'm just going to multiply both sides of the equation to get rid of this radical and this constant here. So let's go ahead and do that. So this will be rewritten as this integral with respect to dx is equal to whatever was in the denominator here. So sigma times the square root of 2 pi. And what I'm going to do is I'm going to square both sides of this equation. And you might be wondering why I'm kind of going through and doing these weird arbitrary steps. And you'll see here in a moment in that squaring both sides of the equation is actually what allows me to use, convert to a polar coordinate system and actually be able to evaluate this integral. Right now, this integral is incredibly hard, well, not even possible really to evaluate because of this x squared term here in the exponent of e. So continuing through, we said we were going to square both sides of the equation. So 1/2 x squared over sigma squared with respect to x dx squared. Okay, and once I square this side, this would become 2 pi sigma squared. Okay, so let me actually now expand this out a little bit. Oh, I'm out of canvas. Give me 1 moment. Let me expand that. I'll be right back. So if we expand this out, we can write this as the integral from negative infinity to infinity of minus 1/2 x squared over sigma squared dx times this exact same integral of e to the minus 1/2 x squared over sigma squared, okay, dx. And this is still, and you probably can't see that. Hang on 1 moment. We'll just shift this over a bit to the right. Is equal to 2 pi sigma squared. Okay, you can see that. Awesome. Okay, so continuing through, let's actually here, we're going to make a substitution. So there's actually nothing stopping me from, substituting some arbitrary variable in for x, so long as I also replace it everywhere within this expression. So let me do that. Here, I'm going to let x on this guy right here, I'm just going to say that x is equal to y. And you'll see why I do this in a moment. Okay, so we went through and we made that substitution. Now what I'm going to do is I'm actually going to call upon one of our previous videos. So we actually proved that if you have two definite integrals being multiplied by each other, that you can combine them. And that is referring to this proof that we did up here. We said that, hey, if we find ourselves in a position where we have some two definite integrals being multiplied by each other, that you can actually rewrite that as a double integral of the two. So I'm going to do that. Let me scroll down. And then what I'll do is I'll actually just go ahead and write that out, and I'll cut to the next line. And just to make this kind of easier to understand so that you can kind of see what I'm doing, I might switch over to using this side. I'll start using the green color. Okay, so I've taken the liberty of writing all that out, and now what we can do is we can use the law of exponents to combine these. Okay, so let's go through and do that. So this is equal to the integral from minus infinity to infinity times the integral from minus infinity to infinity. And when you multiply two exponents, it's the same thing as adding them. So what we can do is we can say this is e to the minus 1/2. And then I'm actually going to factor some stuff out here. Sigma squared. Okay. And now this is going to be x squared plus, and then y squared here. Okay, dy dx. And at this point, you're probably realizing that, okay, there might be an opportunity to do a transition to a polar coordinate system, right? That's what this x squared plus y squared is here, and is why we've kind of done all the work that we've done to up till this point. And the reason being is because once we do this conversion to the polar coordinate system, it actually makes this integral possible to evaluate. So let's go through and do that. We'll go ahead and say that x squared plus y squared is equal to r squared, okay? And we'll also say that dy times dx is equal to, actually I'm going to make this a lowercase r squared, and we're going to say that dy times dx is equal to r dr d theta. And if any of this kind of seems kind of out of the blue, then refer to that video from Professor Leonard. This is where all this stuff gets covered. So I'm going to go through and make these substitutions. In addition, actually, let's just make those substitutions. So let me skip ahead and rewrite this with the substitutions having been made. Okay, so I've gone through and I've written some of that stuff out. And what I want to kind of just draw attention to here, this was the spot where we left off before I kind of cut out and decided to write these other two things, is that when you change the variables of integration with which you're integrating with respect to, you need to change your bounds of integration. And when we do ultimately go through and we change the bounds of the integration for this integral, what we'll end up with is that theta will be going from 0 to 2 pi, and r will be going from 0 to infinity. Again, if this stuff seems kind of weird or unfamiliar, please make sure to watch that video from Professor Leonard. He covers this very well. So we get to this spot now, and we have the integral looking in this form. And the thing that's really nice about this is that this here is actually an integral that we can evaluate. And actually, one thing I've gotten a little bit lackadaisical about is I haven't been writing what this is equal to. But if I just scroll up a little bit here, we can see that this is still all equal to 2 pi sigma squared. So let's do that. Say that this is equal to 2 pi sigma squared, which this is also equal to 2 pi sigma squared. And now I'm actually going to go through and I'm going to evaluate this integral because it's possible. If we do a u substitution, we'll actually end up being able to evaluate this integral, and it'll evaluate to the following. Let me confer with my notes here just so I don't write it down wrong. Okay, minus sigma squared times e to the minus r squared divided by 2 sigma squared, where this goes from 0 to infinity. Okay, and this is all equal to 2 pi sigma squared still. Okay, so one thing I want to do immediately is I want to cancel out these sigma squareds, and I also don't want to drop my, we just did the integral with respect to r, but we still have this d theta for the outer integral, so I don't want to forget to write that. So let's take one more step here and actually evaluate what this kind of middle term So this is still, and I'm actually just going to pull this negative out. So this is still the integral from 0 to 2 pi of, so e to the, and remember we're substituting in for r here, not sigma. So here, r is, if we, eventually putting in infinity in for r squared, this will end up being e to the minus infinity, which is 0, okay, minus, okay, and then if we end up putting 0 in for r squared, that gives us e to the 0, which is 1, okay, times d theta is equal to 2 pi, and now we're finally getting down to like close to the end of this integral. So thank you for bearing with me. If we were to, evaluate this is just -1, this stuff in the square braces, and this is just a negative here, so that simplifies down to just +1. So I can rewrite this as the integral from 0 to 2 pi of d theta, which is equal to 2 pi. And now this is a super easy integral to be able to evaluate. It's just theta evaluated from 2 pi to 0. I'm sorry. Let me just write it out. If we were to actually go through and do the integral, it would be theta from 0 to 2 pi. That's still equal to 2 pi. And then we could say that this evaluates to 2 pi minus 0. 2 pi minus 0, which is equal to 2 pi. And now we can see that 2 pi is indeed, in fact, equal to 2 pi, which ends up proving the original claim that we wanted to make. So if I scroll, and you might be wondering what that is now at this point, but if we scroll back up to the top, the original claim, okay, was that the area underneath the Dirac delta function, right, that's which is just the normal distribution when mu is equal to 0, is equal to 1. Proven. So there you have it. The whole truth, the full truth, and nothing but the truth for why the area underneath the Dirac delta function is equal to 1.